Hi everyone. This video is the last of the videos in our sequence in which we're reviewing all of the topics from Calculus 1 and Calculus 2 quickly before taking a slower return through the topics later on. In this video, we'll discuss sequences and series, which you likely saw at the end of a Calc 2 course or an introductory real analysis course. In the calculus sequence, we often introduce sequences really only for their use in studying series. They have a lot of interesting mathematical study on their own, but for the purposes of calculus, they're often just sort of a waypoint in later on discussing series, which is ultimately the goal. But let's first spend a little bit of time talking about sequences. A sequence is a function from the natural numbers to the real numbers. And for a sequence A, which we want to think of as a function from the natural numbers into R, we denote A of n by A sub n and the sequence with curly braces. So the sequence curly braces of AN is just the sequence of values. Now, you may alternatively see sequences sometimes defined as an ordered list of real numbers. And that's really the same thing as thinking of it as a function from the natural numbers to the real numbers. It's some list of numbers where there is a first element. That's the element that 1 maps to. There's a second element. That's the element that 2 maps to, so on and so on and so on. And of course, we distinguish sequences from sets. So you can imagine, for example, as sets, uh, 1, 2, if I just take the set 1, 2, 3, as sets, that's exactly the same as the set of values 1, 3, 2. However, as sequences, these would be different because of the different ordering, right? And so when we write a sequence like this, generally what we're saying is this is the thing that 1 mapped to, this is the thing that 2 mapped to, this is the thing that 3 mapped to, so on and so on and so on. So here we would be saying this is the thing that 1 mapped to, this is the thing that 2 mapped to, and this is the thing that 3 mapped to. So while these are equal as sets, as sequences, they are not equal. Now, um, usually from context, it's pretty apparent what we're talking about, whether we're talking about a set or a sequence, but we can sometimes be sort of talking about both at the same time. So occasionally I may be talking about a sequence and I may want to talk about its set of output values, right? Or the set of values of the sequence. So the set of values of the sequence is basically like taking the sequence and saying, I don't care about the order anymore. And so now we're talking about sets. So it can be important to distinguish between those two from time to time because it may not always be readily apparent from context whether we're talking about a sequence or a set of values. In any event, in a calculus course or real analysis course, typically as soon as you define sequences, you start looking at some examples. Right, we can represent sequences in a number of different ways, right? One sort of common way may be to just explicitly write out sort of what the nth term is or write out an equation for A of n. So I could have something like this. And there's a perfectly good sequence. I can also define sequences implicitly, right? So I could tell you that I have a sequence where the next value is, say, 1/2 of the previous value. And if I do that, then of course I have to give some starting value. So maybe I might say that the 0th term is 4, right? But in any event, these all generate nice sequences, right? So this first would generate a sequence where if we start with 0, we'd get 0. If we start with 1, if we then go to 1, we'd get 1/2. If we go to 2, we would get 4/9. Uh, and let's see, if we go to what's next, 0, 1, 2, 3, we would get 9 over 27 over 28. Okay, so on and so on. Down here, of course, we're given sort of the 0th term, or the starting term here is 4. Then the next one, now here, we would say, okay, a sub 1. So when my n is 1, this is 1/2 times a sub 0. So this would just be 2, and then 1, and then a half, and then a fourth, and so on and so on. So we can define sequences in a number of different ways. These are all perfectly good ways of defining a sequence. But primarily, we're going to be thinking today about sort of this first way of defining a sequence explicitly in terms of the n. Now, once you have a sequence, the sort of next natural question to ask is, well, what happens to those sequence values as your n gets larger and larger and larger, right? So in mathematical terms, right, we want to know what is the limit of the sequence. So we can define the limit of a sequence. If we have a sequence an, then L is the limit as n goes to infinity of an if and only if for every epsilon greater than 0, there is a capital N, such that whenever little n is greater than capital N, it must follow that the difference between an and L in absolute values is less than epsilon. Sort of said informally, we say that the sequence an approaches L if I can get an as close to L as I would like by going far enough out in the sequence. So if I can go out far enough in the sequence to get an however close to L you want, then it must be that an in fact converges to L. So again, if that limit exists and is equal to L, we will use this terminology that the sequence converges or converges to L. If a sequence does not converge to any real number, then we just say the sequence diverges. And there are a number of ways that can happen. It could be that the sequence values are running off to infinity. So take, for example, the sequence an is equal to n squared. That's a sequence that diverges. But it's also possible that the sequence values just never settle down. So take, for example, a sub n is equal to sine of n. So I have sequence values that are sort of bouncing around between -1 and 1 without any real pattern, but they're never settling down to any fixed value. So both of those would be examples of sequences that diverge, although one of them is bounded and the other is unbounded. There are sort of multiple ways a sequence can diverge. Now, if you're looking at this and maybe thinking back to a previous sort of analysis course, you may notice that this looks fairly similar to how we would define the limit as x goes to infinity of a function f of x from R to R being equal to L. So we would say that this happens if and only if for every epsilon there exists a capital N. Although, again, in this case, because we're dealing with a function over here from R to R, we may just require that this be a real number. There exists a real number, capital N, such that whenever x, again, now I'm thinking of a real variable x, is greater than that capital N, it follows that the absolute value of f of x minus L is less than epsilon. So again, you look at these and they look very similar. And so it's tempting to sort of think, oh, well, these are just equivalent definitions, right? So maybe it doesn't really make a difference whether if I have a sequence, say, a sub n, let's go back to that previous example, n squared over 1 plus n cubed. Like, do I really need to think about it as a sequence of values? Or can I almost really just think of this as a function, right? This is defined for every real value of n. Could I just think of this as a function of a real variable and think about its limit here? We need to be a little bit careful. It turns out if you're just worried about the sequence, it is perfectly okay to think about the associated function and just calculate the limit sort of in the standard way. However, if you are thinking about a function, then you need to be careful because just because you have a function, uh, just because you have a function so that at every integer value that sequence is converging, that does not imply that the function converges. So it is the case that if the limit as x goes to infinity of f of x is equal to L, then if I look at the sequence, so now I'm only taking integer values here of f of n, that limit will also be equal to L. However, the converse is not true. It is not true that if the limit as n goes to infinity of f of n is equal to L, that the limit as x goes to infinity of f of x is equal to L, where I'm thinking here of this as being a real variable, and this is just for integer values of n. Okay, and in fact, this is a problem that I'll probably ask you on a homework to demonstrate the converse is not true by finding a counterexample. So again, the notion of sequence convergence and sort of limits of functions, they're very closely related, but they're not equivalent. So we do have to take a little care at times when dealing with these things. Now, unsurprisingly, you write down a limit definition, it turns out you get lots of nice algebra of sequence limits things. I'm not going to spend a lot of time on these because if you look at them, they're exactly like the algebra of function limits. I can pull constants out, I can break the limit up over a sum or difference, I can break the limit up over a product, and I can break the limit up over a quotient provided that the quotient in the denominator, the limit in the denominator is not zero. So again, I get very nice sort of algebra of sequence limits that are very helpful. Now this turns out to be really helpful, right? When you want to do something like calculate, say some limit like this. So let's say I had 2n cubed plus 4 over 3n cubed plus 4n squared plus 1. Okay. Now, some of you may have sort of memorized properties of rational functions. So for example, one way to deal with this is to look at this and go, well, this is just the function. So if I take f of x, let me be careful here. So one way to think about this is to say, well, if I took the function f of x as 2x cubed plus 4 over 3x cubed plus 4 x squared plus 1. This is a rational function. I'm thinking of this now as a function of a real variable. And maybe I just know that rational functions of this form have horizontal asymptotes. In this case, because the numerator and denominator are the same, that I get an asymptote at the leading coefficient. So I know then that the limit as x goes to infinity of this function f of x is equal to 2/3. Therefore, since the function limit exists, this implies that the limit as n goes to infinity of f of n, which is just this down here, is also equal to 2/3. And that's one perfectly good way to think about this. On the other hand, I might just want to sort of convert this into something simpler. So what I'm going to do is I'm simply going to multiply the top and bottom here by 1 over n. So if I do that, 1 over n cubed over the highest power. So that will give me then that this is equal to the limit as n goes to infinity of 2n cubed over n cubed plus 4 over n cubed over 3n cubed over n cubed plus 4n squared over n cubed plus 1 over n cubed. Okay. Now, I can simplify all of this a bit. Right? So if I simplify this, excuse me, a limit as n goes to infinity. So right now I'm just doing some algebra on the thing I'm taking a limit of. I'm not using any limit properties yet. So this will become 2 plus 4 over n cubed over 3 plus 4 over n plus 1 over n cubed. Now I can take the limit of this quotient by taking the limit of the top over the limit of the bottom, although I have to make sure the limit of the bottom doesn't come out to be 0. And then each of these is a sum. I can take the limit, I can break it up over the sum. So I end up just taking a limit of each term. So that's 2 plus 0 over 3 plus 0 plus 0, which of course gives me 2/3. So again, here I'm just using those algebra of sequence limit properties. So again, these come to be very handy anytime you want to actually calculate the value of some sequence limit. Now, as we go further in the course, we will come back to some additional theorems that we're not going to mention yet that help us determine whether a given sequence converges or diverges. So there are theorems like the monotone convergence theorem, other types of theorems that will help us determine that. But for the time being, we just really want to remind ourselves what a sequence is and some of the very basic properties. Now, actually, as I mentioned earlier, really our point in a calculus course of introducing sequences is really to help us understand what we mean by series convergence. So first, just definitionally, right, a series, I'm just thinking of this infinite sum. So if I'm just expressing this series, right, I'm really just thinking of this as being, say, a1 plus a2 plus a3 plus so on and so on and so on. And what we do is we say, well, this series, if I want to make sense of that infinite sum and whether or not it even like converges to some value, then I need to define what I mean by that. So we say a series is convergent if the sequence of partial sums, so I'm going to define this sequence b sub k, if that sequence is convergent, then I'm going to say that the series is convergent. Now, what is this b sub k? Well, this b sub k is just the sum of the first k terms. So this would just be like, this is a finite sum, which would be a1 plus a2 plus a3 all the way up to a sub k, right? And so for each k from 1 up to infinity, right, I can define this sequence of partial sums, and therefore I'll look at that sequence of partial sums to determine whether or not this series converges. So to give you sort of an example here, so here's a fairly common sum. This is called the harmonic series. So if I was interested in determining whether or not that series converged, I would start defining this sequence. So B1, right, would be the sum of the first 1 terms. It's just the first term. That's 1. B2 would be the sum of the first 2 terms. So it would be 1 plus 1/2. B3 would be the sum of the first 3 terms. It would be 1 plus 1/2 plus 1/3. B4, right? You get the picture. It's the same thing, right? We keep going. So what I can do, right, in this case, I could calculate each of these values. So, okay, B1 is just 1. B2 would be 3/2. B3, let's see, that'd be 3/2, which is 9/6 plus 2/6. So give me 11/6. Okay, and then what I'm going to do is I'm going to look at now this sequence of values. So this is giving me this sequence of values, and I'm going to ask myself, does this sequence converge or diverge? Now, in this particular case, it's really hard to tell, right? And I also can't write down a general expression for the kth term, right? I can't write down some expression in terms of k where I could look at that and say, well, what happens as k goes to infinity? I can't do that. So this is a little harder to deal with, but in fact, this series will diverge. It's a good one to have sort of in your back pocket. The harmonic series diverges. And Again, it's sort of hard to see here in part because it diverges very slowly. So there's sort of a famous quote, and I'm forgetting who to attribute it to now, that essentially says uh, that the harmonic series diverges in theory, but not in practice, because in order to get this sum to be very large, you have to go way, way, way further out in the sequence of partial sums than you might otherwise imagine. So it diverges very slowly. It's essentially the divergence is like logarithmic. So it's just growing very, very slowly, much in the same way that the limit as n goes to infinity of natural log of n is infinity. It's just takes a long time for it to get very large. So we define this series convergence in terms of convergence of the sequence of partial sums. Now, we further sort of classify convergence into two types. So we talk about absolute convergence and conditional convergence. So we say a series is absolutely convergent if the series where I then take the absolute values of every term converges. Uh, if you have a series an which converges, but the series of absolute values diverges, then we say that that series is conditionally convergent. Now, let me make sort of a couple remarks about this before we look at a couple of examples. Um, the first thing you'll notice is that just like structurally, these sentences look a bit different. Um, Up here, this doesn't say anything about whether the series AN converges or not. It just says that the series absolute value of AN converges. By the absolute value test, if this converges, then this converges. Okay, so really you could rewrite this to say if the series AN converges and the series absolute value of AN converges, then we say it's absolutely convergent. But that would be sort of repetitive because as soon as you know that this series converges, this one must converge. However, the converse of that is not true. So if it is possible that this diverges, but this converges. It's also possible that this diverges and this diverges. But we're only going to talk about convergence of this thing if it converges. So if this converges, but this diverges, then AN will be called conditionally convergent. Now, if we're going to define something, there must be some reason. So the question sort of immediately becomes, why do we care about this? Well, let's take two series and look briefly at them. So these are going to look very similar. And along the way, I should mention, I'm applying a lot of series convergence tests you may have seen um, earlier in a calculus course, but it may have been a while. I'm also going to link out to some videos that I created for my online Calculus 2 course that will walk you through some of those more in depth. If you want to see some additional examples, you can jump around and find those. If you want a full-blown lecture on the topic, you can look at that. But I'll link to those also as just a resource. It's not going to be important right now that you have all of those memorized, but if you just want a little bit of a refresher, those will be available to you as well. Now, looking at these two series, if I look at this series, okay, this converges by the alternating series test. This also converges by the alternating series test. So I know that both of these converge. Okay. The question then becomes, okay, great, they converge. Do they converge absolutely or conditionally? So if I want to know that, then I need to look at the associated series where I take the absolute value of the terms. And I can simplify each of these a bit. So here, if I take the absolute value, the only thing that's happening is the sign here is flipping back and forth between -1 and 1. right? When n is 1, this is -1. When n is 2, this is 1. When n is 3, it's -1. When n is 4, it's 1. So this in absolute value is just always 1. The bottom n, it's a natural number. It's always positive. So I can simplify that. I can do something similar down here, right? And I'm just going to get 1 over n squared. Now, if I look at these series, we've already talked about this. This diverges. That's the harmonic series. It diverges. This series, however, this is a P series. So when we talk about P series, we're talking about any series where the terms are of the form 1 over n to the P. Those series converge when that P value is greater than 1. Since 2 is greater than 1, this series converges. And so now going back to the original series we were thinking about here, this series converges, but when I take the absolute values of the terms, that series diverges. So this is conditionally convergent. Whereas this series converges by the alternating series test, and also the series of absolute values of the terms converges. So we say this is absolutely convergent. Now, that's great, but what does that really mean? Like, why do we care about this? Well, there's a very important theorem for series that we'll talk more about in depth later called the Riemann rearrangement theorem. And it sort of says a couple of things. The first is that if we have an absolutely convergent series, we can rearrange the order of the terms and it does not change the value. And you might think, well, normally 1 plus 2, addition's commutative, right? 1 plus 2 is the same as 2 plus 1. So that it should never matter, right? For any series, I should be able to reorder the terms. That works for finite sums. However, for infinite sums, that is not necessarily true. It's only true if the series is absolutely convergent. So in this case, I could rearrange the terms and I would get exactly the same value back. So if I were to just think about this series, say writing out some of the terms, right? So this would be -1 plus 1 over 4 minus 1 over 9 plus 1 over 16, so on and so on. I could do sort of any rearrangement of these terms I want, and I'll still get the same value. So maybe I want to split apart all the positive and negative terms. So maybe I want to put all the negative terms up front. Arthur's dying on me. And, and then I'll keep all the positive terms together also. Okay. And notice I could actually express each of these as sums. Right? So I could factor a negative out here. This is the sum of the reciprocals of the even square, or sorry, of the odd squares. So I could write this as n equals 1 to infinity of 1 over 2n minus 1 squared, plus this sum, which is n equals 1 to infinity. So if I look at these terms, these are the reciprocals of the even squares. So this would be 1 over 2n squared. And because this series is absolutely convergent, I know that this sum has to be equal to this sum. Okay, because I'm allowed to rearrange things for absolutely convergent series. Now, the other part of the Riemann rearrangement theorem, though, tells you that for conditionally convergent series, when you start switching terms, you could start changing the value. In fact, it says actually even a little bit more than that. It says that you could rearrange this series to make it converge to any real value you wish. So we could make this converge to 7 and 12 and 52 and the natural log of 17 and negative 30. Like you could rearrange this series in such a way that it converges to any number you want. So any other rearrangement of these terms need not be equal to this particular arrangement. So if you try to start doing something like this, right, you could write out, okay, the first few terms, but then it's not justified to rearrange them as we did in this step here. So what you could rearrange it, but you wouldn't have an equality anymore because the Riemann rearrangement theorem tells you that's probably gonna change it to some other value. So we'll talk more about absolute and conditional convergence when we get a little further along. There are some important consequences, as I've sort of mentioned about that. But it's just for now something to remind yourself of this distinction and just to be a little bit careful anytime you're dealing with series that have positive and negative terms. Notice that any series that only has positive terms, well, if it converges absolutely because well, the absolute value of the terms are just the same as the original terms themselves. So this is really only something we worry about when we have series that have both positive and negative terms. All right. I just briefly wanted to remind you, we've mentioned some of these, but I wanted to sort of remind you of some of the tests for convergence that you would have seen in a calculus and maybe discuss further in an analysis course. So I've broken these down into sort of some groups, but we'll talk about those in a minute. So you may have seen geometric series, that's a special type of series, or P series, which I mentioned earlier. So these two, they're really just sort of special forms of series. And because they have special forms, we often have, uh, we have ways of knowing whether these things converge or diverge. So for example, if I have a geometric series, if I was to take geometric series, a geometric series is always of the form AR to the n, say n equals 0 to infinity. And this converges if and only if the absolute value of R is less than 1. Okay, so it diverges if R is greater than or equal to 1. So same thing, P series I mentioned earlier, it's of the form 1 over n to the P. You know that converges if P is greater than 1 and diverges if P is less than or equal to 1. The integral test, the ratio test, the root test, absolute value test, alternating series test, these are all tests we'll talk more about in depth a little later on. The integral test is sort of its own special case. It really relates series to Riemann sums to integrals. And so sort of through that connection helps us to determine whether something converges or diverges. Ratio and root test, they're really sort of special types of they're comparisons to special forms. So for example, the ratio test is really looking to see if your series, as you go out far enough, is behaving like a geometric series. So for the ratio test in particular, we look at the limit as n goes to infinity of the ratio, the absolute value of the ratio of successive terms. So we look at this limit, right? Note that for a geometric series, this would be, for a geometric series, this ratio would be AR to the n plus 1 over AR to the n, which would just simplify to be R. Well, sorry, absolute values, and so we get absolute value of R. We know this converges if this is less than 1 and diverges if it's greater than or equal to 1. We do something similar here, looking at this limit, although we have to be careful about what happens at 1. Actually, it's inconclusive for the ratio test. So my point is, don't worry about the details right now, but the whole point of these tests is to compare to other sort of special forms. So basically say, well, in the limit, yeah, it's maybe not a geometric series exactly, but in the limit, it's behaving like one, and therefore I can say something about that. These last two tests I have stuck on here because these are tests, all of these previous tests really work. Well, the special forms are one thing, but these other tests, uh, you have to be a little careful sometimes about signs. These tests are really the ones that sort of specialize in thinking about series with positive and negative terms. Now, ratio and root tests can also apply there, but these are really the ones that I think of for series with positive and negative terms. And in particular, I think about them because these are typically the ones you're going to use to determine absolute versus conditional convergence. So for positive and negative terms. So again, I would encourage you to maybe go review these if it's been a while and you don't quite remember them. Again, I've linked to some videos elsewhere that will have more information about this. But it's again not critical, but probably worth reviewing at least a little bit to make sure you remember these things. Now, again, sequences are interesting in their own right, series are interesting in their own right. But one of the big motivations for even talking about series to begin with is because we want to talk about a slightly different kind of series, which is the power series. So much of the theory that we will sort of build up for series eventually becomes even more important in the context of these power series. Now, the idea first is I could define a function of x in this way. So for any particular value of x, this would just be a series of real numbers. So you can determine, the first sort of question you might ask is, for what values of x will this series converge? Okay, so that might have been where in Calculus 2 you learned about things like radius of convergence or interval of convergence. Those are all associated with that question. You might then also ask, well, can I choose my cn's in a particular way to make this some particular function that I know? So maybe I want to come up with a series who, when I plug in any x, what I get out is sine of x or cosine of x or e to the x. So that's the theory of Taylor series and Maclaurin series that you might have seen in a calculus course. Finally, you might want to start asking, let's say I could do that. Let's say I could come up with a series that, so that sine of x was equal to this series, power series representation. Can I then differentiate both sides? And should I expect that those will still be equal to one another? Can I integrate both sides? Can I do it term by term, right? So if I want to take a derivative of this, it'd be really nice if I could say that the derivative with respect to x of this sum I'd really like to be able to say I can just differentiate this term by term. And you might, again, in the back of your head, you might be saying, you can always do that, Quinn, right? Like you can break up derivatives over sums. Well, you can always break up derivatives over finite sums. Whether or not we can do this for these sorts of power series, well, that's an open question for now. That's something we're going to have to deal with. Same with integration, right? Can I do this with integration? In general, no, you can't break up derivatives over infinite sums, but these aren't just any kinds of infinite sums. These are special types of infinite sums called power series. And so we will prove some results related to that later in the course towards the end of the semester. So that brings us to the end of this video and to the end of our sort of quick review of calculus. Starting in the next video, we will begin a second pass through this material, but going much more slowly. And in particular, one of the things we're going to do is pay attention to some cases that would almost certainly have been overlooked in a calculus course. So often in a calculus course, you're taking functions that are defined on nice big intervals. It's sort of a really nice domain. But we might want to know what happens if I take a function whose domain is, say, the set of values of the form 1 over n, where n is a natural number. Well, now that domain has a bunch of isolated points, but then they're sort of their values in the domain that are converging to zero. What does that have to do with anything? Can I talk about a limit? Can I talk about a derivative in that case? So we're going to go back and deal in much more detail with defining these things in the most general context that we can, and understanding in those sort of fringe cases or those more complicated cases, how we can still compute things like a limit or a derivative, how we can prove things about limits or derivatives or integrals or power series or whatever it may be in the most general cases possible.